This is section 2.5, continuity, and our first objective is to understand the definition of continuity in both an analytic and a graphical context. So, when we're done with this objective, I want you to be able to discuss the difference between a function that is continuous at a point and a function that has a limit, because they are connected, but they are not the same thing. So if we look here at this vocabulary, it says a function is continuous at a number a if the limit as x approaches a from both sides equals f of a. So we need to kind of break that down and see what this is telling us. It says f is continuous if f of a is defined. Now last year, and probably in your Algebra 2 classes, you learned that if you plug a into a function, you would get the output out, which was f of a, and that would correspond to some point on the curve whose x-coordinate was a and whose y-coordinate was f of a. So, in order for f to be continuous, the first thing that has to happen is you have to be able to plug a into the function and get an output. So you've got to have it be in the domain. The second thing is the limit as x approaches a from the left-hand side has to be the same as the limit as x approaches a from the right-hand side. If you recall, back when we talked about limits, in order for a limit to exist, it had to approach the same y value from the left and from the right. That means from this point here, coming at it toward the right, I'm going to head toward the same y value as I am heading toward it from the left. Now the third thing, and this is what makes the continuity work for us, is that two-sided limit, in other words, the L or the y coordinate that your function is approaching as you let x get closer and closer to a from both sides, that y value that you're getting close to is the same as the y value that is assigned to the function by f. So the output of the function will be the same as the limit. So I want you to explain in words what you can see on the graph at x equals a if the function is continuous at x equals a. So you will notice that we will often talk about continuity using layman's terms. That says a function is continuous at x equals a if you can jump on the curve to the left of a we'll put x equals a, and then continue past x equals a without picking up your pencil. So pretty much every time you have to pick up your pencil, you have hit a discontinuity. So as long as you aren't picking up your pencil, you will be continuous. So if we look at this particular illustration here, we can see that there are several places where we have to pick up our pencil. And when we pick up our pencil, we have encountered a discontinuity, and there are several different types. So if I'm traveling along here, I see that I start to do this crazy wild oscillation, and right at -8, I've got a weird hole, and it stems from an oscillation. So in this case, we have an oscillating discontinuity happening at -8. If we continue along our curve, we don't have to pick it up until we hit -4. And when we hit -4, in order to continue, we have to pick up our pencil and move it down to this piece of the graph. So at -4, we had to jump from one y-coordinate to another y-coordinate. So this would be considered a jump or a step in the piecewise function. So now we'll continue along. Again, here we have a hole, so we have to pick it up. But notice that we come right back down in almost the same place. So we didn't really jump because we didn't change drastically between y coordinates. We just had a tiny little gap that we had to hop over. So this one is called a removable hole in the graph because I could fix that problem if I just drew one point. So now here we can see that we've got two different types of removable holes. One says A is not in the domain and the other says A is in the domain. So if A is in the domain, that means you can plug A into the function and get a y coordinate. That means you have a point on the graph whose x coordinate is A. And if we look here, we can see there is no point on the graph that has that x coordinate of A. So in this case, it's a removable hole in the graph with A not in the domain. That happens when x is -3. If we continue along the curve at -2, we again have to jump in order to pick up where we pick up and continue along. So at -2, we have yet another jump. And now we continue along, don't have to pick up our pencil until we hit 1. And at 1, again, we see that same little gap that could be fixed by a single point. So we are at a removable hole, only this time we can see that there is a y coordinate of -2 assigned to the x coordinate of 1. Because of this, we know that that +1 was in the domain of the function. So we have a removable hole where the hole has an x coordinate in the function's domain. And then the last time we have to pick up our pencil is when we start heading down on this asymptote and then we pick back up again. So this particular discontinuity at 4 is called a vertical asymptote or an infinite discontinuity. We have some additional vocabulary. The first one says continuity from the right. And that says a function f is continuous from the right at a number a if, as x approaches a from the right-hand side, the y coordinates that you are approaching is the same as the y coordinate assigned to a. So graphically, that means I will be traveling along a curve from the right, and then I will hit the y coordinate that was assigned to a. So this would be a comma f of a. If we look here, continuity from the left, we have the same thing except instead of approaching that point from the right, I'm going to approach that point from the left. So in this case, we would have curve coming off the left tail, and again we'd have an x coordinate of a, and our limit would run into that y coordinate f of a. So, for example, if we look at the function f of x equals this greatest integer function, or our step function, we can see that we have to pick up our pencil at every single interval. So this would be f has discontinuities at all integers. Else didn't quite go up. Then f will be continuous from the right. That means we're looking for a curve that runs into closed circles. So that's going to happen everywhere if we're running into closed circles coming from the right. So this is all real numbers. And will be continuous from the left. That means we have curve coming and hitting points from the left. We can say we're continuous at the left at all real numbers except the integers. Because if we're trying to travel toward the might help if I spell correctly. Integers. If we're coming toward an integer, as soon as we hit that integer, we have to pick up our pencil, and we don't hit the closed circle when we're coming from the left, whereas everywhere else we're hitting all these nice points in between. We can get to there either from the left or the right, anywhere in between an integer. It's only at the integers that we have continuity just from the right and not from the left. So the next vocabulary is continuity on an interval. We can say that a function f is continuous on an interval if it's continuous at every number in the interval. In other words, if you can pass through, let's say I have an a and I want to get to b, that means graphically from a to b, I don't ever pick up my pencil. And as long as I don't pick up my pencil, here on the left I'm continuous from the right. Here on the right side I'm continuous from the left, and everywhere in between I don't pick up my pencil. So this function f would be continuous on the interval from a to b. So this leads us to a theorem that says if f and g are continuous at a and c is a constant, then we can create new functions that are also going to be continuous. And what's nice about this theorem is that it just reinforces what our gut instinct would tell us. If you have nice functions, then you can do operations with those nice functions without screwing anything up. So I could add functions, they'll still be continuous. I can subtract them, I can multiply them by a constant, multiply them together, or I can divide as long as I do not create domain problems. Remember, domain problems occur when you try to divide by 0, when you try to take the even root of a negative number, or when you try to put a non-positive inside logs. So if all of these are behaving well, that means they don't have any of those domain problems. So as long as we don't divide by 0, then this quotient will also work for us and be continuous. Now the upshot of this is that if I take any polynomial, then I can do whatever I want with it and it'll still be continuous. The next one says rational functions. Well, we might think of a rational function as, say, a 1 over x, and we know that has an asymptote at x equals 0. But if we read this, it says they're continuous at every number in their domains. And notice that 0 is not in the domain of this function because it would cause me to divide by 0. So what do you know? We get a discontinuity at the same place that we had a problem with the domain. You will find that that is the case for all of these. The only time you have to pick up your pencil is when you have a domain problem. So there's a very close relationship between the continuity and the domain. So our final two theorems say if f is continuous at b and the limit of g of x as x approaches a equals b, then, well, what am I doing here? It looks like I'm taking something that is nice and something else that is nice, and instead of adding, subtracting, multiplying, or dividing, I am now composing. And if we look carefully, it looks like I took this limit and put it inside and computed this limit of g of x, which was b, and I can just get the output. So that gives us another nice benefit of limits and continuity, is that I can pull that limit inside and outside of the functions without causing any problems. Same thing here. If g is continuous and f is continuous at the output of this one, then we can compose those functions and not screw anything up. So based on these theorems and corollary, I would like you to predict when a function would not be continuous and then write down your prediction right here. Hopefully you saw the relationship between continuity and the domain of a function, and you realize that discontinuities occur only at problems in the domain or at joints on a piecewise function. So based on that relationship, we can now look at examples 2 and 3. Example 2 says, where are the following functions continuous? And we want to justify the conclusion with a graph. So these functions will be continuous on their domains because I'm just composing other continuous functions together. So that means as long as this is defined, I won't have any problems with my continuity. Now, according to our trig that we did back in pre-calc and probably algebra 2, we could plug anything we wanted into a cosine, and we can also cube anything. So there are no problems anywhere. We don't have division by 0, we don't have logs, we don't have even roots. So this is going to be continuous for all real numbers. We can see that if we look at the graph. Here is that cosine of x cubed. We can see that we never have to pick up our pencil. It's just going to start oscillating faster and faster as we move out. So this graph verifies that we're continuous on the real numbers. We don't ever have to pick up our pencil. So I will let you sketch that graph on your notes, and then we'll pick back up again. So if we look at part B, we have to consider our domain issues, which are division by 0, even roots, and logs. And in this particular problem, we see that we have a log natural. We know or remember from our pre-calculus that the insides of logs have to be positive all the time. So that would mean that sine needs to be less than 1. Well, sign is less than 1 everywhere except when sign equals 1. So we will be continuous on the real numbers except when sign equals 1. And that happens at pi over 2 plus multiples of the period of sign. So k would be an integer. So what we will anticipate seeing on the graph of this function is that we have to pick up our pencil at pi over 2 and 5 pi over 2 and negative 3 pi over 2. And if we pick up our calculators and graph that, we can see that exact same thing. Here we have we've got an asymptote right here at negative 3 pi over 2. We've got another asymptote here at pi over 2. We would repeat if we continued, and every single time we'd see these asymptotes showing up on our calculator. So I will let you graph that picture. It'll look a little better than what I have on my screen, and do that now. With example 3, it asks, where is this function going to be continuous? So the function will be continuous as long as we don't abuse any of our domain criteria. So that means we cannot divide by 0. So x squared minus 4 cannot equal 0, which means x squared cannot equal 4, which means that x cannot equal plus or minus 2. So that's one piece of the real number options that we have to throw out. We also see up here that we've got a log. Well, logs require that the insides always be positive. Tangent inverse, if you remember your graph of tangent inverse, looks like a tangent turned on its side, and it never has a problem. You never have to pick up your pencil. So this one, the domain is all reals. So if we put all of this together, we know x has to be positive and it can't be 2. So our continuity starts at 0, continues on to 2, and then picks back up again from 2 to infinity. So I want to remind you about this notation because mathematics is notorious for having one notation represent multiple things. So in this particular case, we are using these parentheses not to designate ordered pairs, but to instead tell us what the domain is in interval notation. So a soft parenthesis, a soft bracket says I do not get to include 0, but I get every number from 0 up to 2, but I do not include 2. And then I'm going to, in union or join, tag on to this, the next interval, which picks up after 2, immediately after, really close but not including, and then it continues on to infinity. Now infinity is not really a number, so we can't ever get there. So we would never put a hard bracket or try to include an infinity. We just leave it as is. So take a look at your notes web exam problems and see how many of them you can do on your own without asking me questions. And those you don't know how to start, highlight them and we'll get to work on them tomorrow. Also, I would like you to be able to discuss the difference between a function that's continuous at a point x equals a versus a function that has a limit at x equals a but is not continuous. So this goes back to that definition of continuity. And then tomorrow I would like you to be able to create an algebraic function that has a limit but is not continuous. And then I want you to support that claim with a graph. So why would you have to pick up your pen on an algebraic function if you also have a limit? So support that claim with a graph, see if you can write it.